Good afternoon, everyone. This is our third session today of our FDP on advances on earthquake engineering, sponsored by AICT and Atal Academy. First and foremost, I like to welcome our resource person, Dr. Gigi Anna Varghese, our beloved HOD, Anjali ma'am, FDP coordinator Radhika ma'am, all my colleagues, and all my dear participants. Okay, welcome all. Before starting the session, let me introduce our resource person, Dr. Gigi Anna Varghese, professor who has bachelor's degree in civil engineering from University of Kerala and further specialized in the area of structural engineering and construction management from the same institute. She defended her thesis in 2013 and obtained PhD from IIT Madras. Currently works as professor in Department of Civil Engineering, GEC, Barton Hill, Trivandrum. She served as assistant engineer in irrigation department from 1999 to 2003 and also as assistant professor under Directorate of Technical Education from 2003 onwards. She has published more than 20 papers in various national and international journals and conference proceedings, and also a reviewer of several journal and conference papers. She is involved in structural consultancy works through Center for Continuing Education, CCE, and presently the manager of CCE at GEC Barton Hill. Her area of specialization includes structural dynamics, design of structures, and performance-based design. The third session is on the seismic design of liquid storage tanks, and I again invite all of you to this session. Thank you.
Thank you, Mr. Ben, for introducing me to the participants. And let me share my screen. Is it visible?
Yes, ma'am.
And I think I'm audible also.
Yeah. Yes, ma'am.
Okay. So before starting the session, I would like to express my gratitude to the coordinators of the program, Professor Radhika and Dr. Beena, for inviting me to deliver a lecture in this FTP. And in the last 3-4 days, you were listening to recent advances in engineering seismology, earthquake design, resistant design, construction practices, vibration control, etc. And the concept which you have learned during these sessions will be applied to the design of a very important civil engineering structure, which is a water tank. And in this title slide, I have included 2 photographs. One is that of the left one is that of a ground supported tank, and the right one is that of an elevator water tank. And this presentation is prepared with reference to the IS code 3370 and the IS 1893, both part 1 and part 2 provisions are included. And these are the contents of my presentation. With the help of some performance of some water tanks during past earthquake, we will see what is the significance of doing a seismic analysis and design of water tank. And for those who don't know those who are not familiar with the conventional non-seismic design, I have included 2-3 slides regarding non-seismic design of water tanks also. And as per our Indian standard code, water tanks are idealized as spring mass models, and we have to consider the effect of both horizontal as well as vertical ground acceleration while finding out the design forces like base shear, base moment, overturning moment, and hydrodynamic pressure. So all these topics will be covered during this 1.5-2 hours. And at the end of the session, I will show the evaluation, seismic evaluation of an elevated water tank, which was designed as per the provisions in the IS code. And that evaluation is conducted with the help of nonlinear time history analysis. And this photograph shows the performance or the behavior of an earthquake during 1960 Chile earthquake. And if you look into in detail on what happened to the staging, we can see that cracks have formed in the braces and columns are remaining intact here. So plastic hinges are formed only in the bracing, and the tank remains stable, almost stable like this. So this can be considered as a preferred failure mechanism compared to the failure mechanism which is shown in this slide. That in this photograph, you can see that there is complete collapse for the tank structure. And for this tank, you can see plastic hinges formed in the ring beam column joint, but there is not much damage for the tank structure. And this is another photograph which shows deep vertical cracks in the column. So compared to the first photograph, this failure pattern is not at all preferred while designing the elevated water tank. And you can see cracks in the end of the beam here. So during earthquake, you can say that the design for the tank structure is almost okay, but failure is usually concentrated in the staging. So this shows the significance of doing a seismic analysis in addition to the analysis and design due to hydrostatic effects alone. And in this picture, I have shown a rectangular water tank which is supported on ground and which is having a cover slab at the top. The design forces for the components of the water tank. The components of the water tank are the sidewall as well as the base slab. It depends upon the support condition. Coming to the bottom support condition, the detail is shown in the left side of this slide. And if we are doing a monolithic construction between the sidewall and the base slab with haunch bars provided, we can assume that it is having a fixed base condition. The wall has a fixed base condition. Whereas if you're doing a detailing like this, it is considered as a hinged base, and this detailing corresponds to a flexible base. And this flexible base can be an anchored flexible base, and another detailing here, which is an unanchored, but it is contained within the base slab. And last one, we can say that the wall is supported on the base slab, but it is unanchored and uncontained support for the base for the wall. And coming to the top support condition, if it is an open water tank, we can say that the top end is free. But if you are providing a cover slab for this water tank, we can say that the top has a hinged support condition. So based on the several combinations of support condition, the design actions for the sidewall may change. So we will quickly go through the conventional non-seismic design, which is usually carried out with the help of IS 3370, and it has 4 parts. And first part gives details for the general design details. Second part is for reinforced concrete water tank, and third part is for pre-stressed concrete. And fourth part of the code gives some design charts based on the support conditions for the side wall. We will get coefficients like my and mx so that we can find out what is the horizontal moment as well as vertical moment at critical locations of the side wall. And this is the plan of the water tank, a reinforced concrete water tank. And since it is continuous, side walls are continuous on all edges, we can assume fixed condition at both vertical edges. And based on the bottom support condition, it can be a fixed base or a hinged base, and the top can be a free edge or a hinged edge. And in non-seismic design, the load acting on the sidewall will be hydrostatic pressure. And this hydrostatic pressure variation, all of us know, it is 0 value at the top and maximum of W into A at the bottom. And regarding the base slab, it will be subjected to a uniformly distributed pressure of W into A. And if you assume this side as the shorter wall and this side as a longer wall, When a flexural member is subjected to lateral loading, in addition to bending moment, shear force also occur at the critical section. And we can say that the shear force acting on the short wall is acting as an axial tension for the long wall. In a similar manner, the shear force acting on the low wall has axial tensile effect for the long wall. So we have to design these side walls for the combined effect of axial force and bending moment. And while deciding on the thickness of this side wall, it has to satisfy the interaction equation. This interaction equation is sigma Ct dash by sigma Ct plus sigma C dt dash by sigma bt should be less than or equal to 1. And the denominator shows the capacity in axial tension and flexural tension, whereas the numerator shows the actual value of stresses induced in the tank wall. And if we are satisfied, if the design is satisfying this equation, then we can design the reinforcement of the side wall for the combined action of bending moment and shear force. And assume that it is an elevated water tank, we can apply the various load combinations which are given in IS 456 as well as IS 1893, and we can design the staging also for the combination of earthquake load as well as wind load. This is all about the non-seismic design of water tank. Now coming to the seismic design criteria. The objective of all seismic design is to limit the occurrence of failure. Here it is written, it is unacceptable performance should be limited to a low value. And this low probabilities of failure is to be achieved in a very cost-effective manner. And we know the design involves several uncertainties, and there is uncertainty in the prediction of load as well as capacity. So we can assume several probability distribution function for the variations of loads and capacity. And if using suitable equations, we can do a seismic probabilistic risk assessment, which involves detailed calculation. But for practical design, we don't have to go for such a complicated design procedure. Code helps us to perform a simpler direct approach in order to get a safe design for all structures. And for the seismic design of water tanks, we usually follow IS 1893 Part 2, and also the provisions in Part 1 is applicable for all types of structures. So further discussions on the design of water tank will be limited to IS 1893 Part 1 and Part 2. And we know the latest release of the IS 1893 code Part 1 was in 2016, whereas for Part 2, it was in 2014. Before coming into the details of IS 1893 Part 2 2014, we will see how the seismic design concepts were incorporated in the pre-revised code, that is the 1984 version of the code. So that covers only the provisions for the elevated water tanks. That previous version didn't mention anything about ground supported tank. But the elevated water tank, it can be supported on shafts or bracings like this, or using masonry shafts also, we can see elevated water tanks. As per this version of the code, we can idealize it into a single degree of freedom system with the whole mass, the huge mass, lumped at the CG position of the tank liquid system. And the stiffness for the lateral vibration is provided by the staging. This was the assumption for the earlier version of the code. And we can solve the dynamics of single degree of freedom system to find out the displacement, corresponding base shears, and the moments which are acting at various locations of the staging. Now, In order to incorporate the hydrodynamic effect due to the moving water inside the water tank during earthquake excitation, we should consider both hydrostatic pressure as well as hydrodynamic pressure. And you had already seen the variation of hydrostatic pressure, which is acting on the side wall. It is triangular in shape, and the hydrostatic pressure acting on the base slab, it will be uniformly distributed. But once the water tank is subjected to ground shaking, earthquake gives energy to the fluid, and when it exceeds the initial inertia, the water begins to move. The liquid motion inside the container, the technical term is sloshing. And this sloshing causes hydrodynamic forces on the tank structure. And we can say that hydrodynamic force act on the side wall as well as on the base of the slab. And if we compare with the earthquake effect on a multi-storied building, we usually consider the effect of horizontal shaking while designing multi-storied building. But in the case of water tanks, code specifies that we have to consider both the horizontal ground shaking as well as vertical component of shaking separately, and then we have to combine it in a suitable manner. And to understand what is sloshing, a demonstration is done here with the help of a shake table. If we take water inside a transparent water tank model, and if we excite by giving horizontal acceleration, we can see the top surface of liquid is moving, whereas the bottom portion of water remains in contact with the water tank, and so there is no relative motion between water tank and water which is present in the bottom portion, but there is relative motion of water near to the free surface, and this relative motion is called sloshing. And the total mass of water, if m represents total mass of water, we can divide it into two parts. One is the impulsive mass, which is rigidly connected with the tank wall. Here a rigid link is provided to represent the connection between impulsive mass and the tank wall. Whereas the top portion of water has relative movement compared to the side wall. And we can see the first mode of vibration like this. It can oscillate in this direction or oscillate in this direction. And the stiffness for the convective part will be less compared to the stiffness for the impulsive part. And code gives equations and charts for finding out these three unknowns. In this figure, I have marked three variables. One is the impulsive mass, second is the convective mass, and we know the total sum of impulsive mass plus convective mass will be the total mass of fluid. And based on the equations and charts, we can find out values of Mi, Mc, and Kc. And it is found that this convective part has lower frequencies compared to the natural frequency of the tank liquid system. And hence, it is unaffected by the flexibility of the tank wall. We can say that for an RCC water tank, it is rigid compared to a steel water tank. Steel water tank is flexible compared to an RCC water tank. So whatever may be the material of the container, the sloshing mode is unaffected by the flexibility of the water tank. Whereas the impulsive part, which is present in the bottom portion of the water tank, is sensitive to the tank wall flexibility. And I have already told that the convective part is associated with a lower frequency. And lower frequency means it has higher time period, and this higher time period attracts a very less spectral acceleration compared to a very stiff structure which is having a lower time period. And in order to find out the base shear, we have to find out the horizontal acceleration coefficient. And this horizontal acceleration coefficient depends upon the spectral acceleration value. And this response spectrum is given in IS 1893 part 1. Then this impulsive frequency normally falls in the amplified nearly constant region of the pseudo acceleration response spectrum. If we calculate the impulsive time period, it may come almost in this region, so that it attracts a very large spectral acceleration compared to the convective mode, which has lower frequency or higher time period. So we cannot consider the whole mass as a single unit. We have to consider the effect of moving liquid at the top surface separately compared with the impulsive mass movement which is there in the bottom portion of the liquid. Then total hydrodynamic effects may be obtained by superposing on the impulsive effect those of the fundamental convective modes only. Convective modes have different frequencies, first mode, second mode, and third mode. And the first mode may come around this region, and the higher modes will have a very less influence on the response of the water tank. So while designing water tank, we combine the effects of the impulsive mode as well as the first or the fundamental fundamental mode effect. 1 minute. Okay. This gives the expression for finding out the natural sloshing frequency for a circular water tank. And this natural sloshing frequency depends upon the H/R ratio, height of fluid by radius of the water tank. And assume that this HF/R is equal to 0.5 for a given water tank. We can simplify this equation. And we can find out what is FC1, FC2, and FC3. But the parameter of importance to us is the time period, which is directly related with the frequency. And we can simplify this equation. TC1 for circular water tank having HF/R is equal to 0.5 is given by this equation. This is the second time period equation, and this is the third time period equation. And here R is expressed in feet. And you can see the sloshing modes for the first mode, second mode, and third mode. This represents the first sloshing mode, this is the second mode, and this is the third mode. And greater energy is required to excite it in the higher modes. So usually we consider only the first mode effect in designing the water tank structure. And if we want to extract the natural sloshing frequencies and mode shapes, we can model the tank structure in any of the commercial softwares. We have to model and mesh both the tank as well as the water and do a model analysis. You can find out what is the first natural frequency, second frequency, and so on. And you can see how the top surface of the liquid moves when it is excited with the natural frequencies. Now let us see how we can idealize a water tank using spring mass system. And in the 2014 version of the code, both the design provisions for ground supported tank as well as elevated water tanks are covered. First, we will see the idealization for the ground supported tank. Assume this is the ground supported tank, and D is the diameter of a circular water tank, and L is the lateral dimension of the water tank, which is in the direction of seismic force, and H is the height of the liquid present inside the tank. And as we had seen earlier, we can divide it into two masses, the bottom portion called the impulsive mass, the top portion called the convective mass, and there is one more unknown, which is Kc. And we can find out the values of Mi, Mc, and Kc with the help of IS 1893 Part 2. And knowing these values of Mi, Mc, and Kc, we can find out what is the lateral force, which is Vi, present at this level, Vc, which is a lateral base shear present due to the convective mass. But for design, in addition to these lateral forces, we need the bending moment due to these horizontal forces. For that, we need the height at which the impulsive mass is located and the height at which the convective mass is located. And we can say that the bending moment due to impulsive force will be Vi into Hi. Bending moment due to convective force will be Vc into Hc. And you can see two more variables written here, Hi star and Hc star. And those heights are the equivalent heights if we consider the hydrodynamic pressure which is acting on the sidewall. If we want to calculate bending moment at the base of the sidewall, we can use the term Hi and Hc. But if we want to calculate the overturning moment above this point, then the effect of pressure which is acting on the base slab also comes into play, so that the height may increase. Hi increases to a different value of Hi star, Hc may increase to Hc star. Similar to the two mass idealization which we had seen for the ground supported tank, elevated water tanks are also idealized as two mass system. And this part we know what is Mc and what is Kc. This corresponds to the sloshing mode of water which is present at the top portion. And the impulsive mass we can combine with the structural mass. Structural mass means mass of the water tank and 1/3 the mass of the staging. And just as we have seen with respect to the response spectrum, this convective mass has a lower frequency and this has a higher frequency. And since these frequencies are well separated, we can uncouple the system into two single degree of freedom system, and we can solve the corresponding differential equations to find out the solution for the behavior of water tank, elevated water tank also. Here, Ks is the stiffness provided to this mass, Mi plus Ms, and this stiffness is provided by the supporting staging. And for all vibrating structures, we know damping is also present. And damping reduces the amplitude of vibration. And we have to quantify what is the damping for the convective mode and what is the damping for the impulsive mode. And since impulsive mode is rigidly connected to the water tank, we can assume the same damping coefficient for the impulsive mass as that of the supporting water tank. Whereas convective mode has a different damping ratio, which is lower compared to the damping coefficient for the impulsive mass. So as per the code, we can assume a damping ratio of 0.5% for the convective mode. And if it is a reinforced concrete or a masonry tank, the damping coefficient can be 5%. And for a steel tank, the damping is 2%. And the spectrum which we had seen earlier is plotted for a damping of 5%. So if we want to apply it for a different damping value, we have to apply a multiplication for 1.4 for the impulsive mode and 1.75 for the convective mode. For doing lateral load analysis, equivalent static analysis, we have to calculate the base shear. And this base shear, the common expression is AH into W, where AH is the horizontal seismic coefficient and W is the seismic weight. And the equation for AH is Z by 2, I by R and SA by G. And all of you may be familiar with all these variables. Z is the zone factor, I is the importance factor, R is the response reduction factor. And SA by G is the spectral acceleration coefficient. And this SA by G is different for the impulsive and convective modes. We have to calculate two AH values, AHI for the impulsive mode and AHC for the convective mode. So we calculate base shear separately for the impulsive mode and convective mode and then combine using SRS's combination to find out the net base shear acting on the tank structure. And this is all about finding out the lateral load for doing an equivalent static analysis. But we know when a water tank is excited, in addition to the hydrostatic pressure distribution, this all of us know it is triangular in shape. The sidewall as well as the base of the tank will be subjected to hydrodynamic pressure also. And while designing, we have to consider the hydrodynamic pressure also if it is subjected to earthquake forces. So let us see what is a variation of hydrodynamic pressure on the sidewall as well as on the base slab. This hydrodynamic pressure can also be divided into two parts, one due to the impulsive pressure or due to the movement of impulsive mass, and second due to the convective mass. And this represents the distribution pattern of the impulsive hydrodynamic pressure and convective hydrodynamic pressure acting on the sidewall. And we know impulsive mass is located towards the base. So maximum value of impulsive pressure occurs at the bottom, whereas it is zero at the top. Whereas the convective pressure is due to water present at the top surface. So its value is maximum at the top and it has a minimum value at the bottom. And we can see a non-linear distribution for both the hydrodynamic pressures which are acting on the wall. And we can locate the centroid of this pressure diagram and let it be at a height HI and HC from the base of the sidewall. And this base slab is also subjected to hydrodynamic pressure. And if you look at the variation of hydrodynamic pressure acting on the base slab, it resembles the first mode shape of the sloshing mode. Due to the impulsive pressure acting on the base slab and due to convective pressure acting on the base slab, there is a tendency of overturning moment at about the base of the wall. So we have to consider that effect also while calculating or while checking stability of the structure, both the ground supported as well as elevated water tank. And so if we are considering this effect, automatically the CG position of this pressure distribution increases. HI increases to HI star and HC increases to HC star. And this is the distribution for a water tank which is containing liquid. But sometimes if it is a very huge water tank, we usually provide columns and shafts or baffle walls inside the water tank. In that case, the code says that the effect of sloshing or the convective pressure increases, whereas the impulsive pressure increases. Convective pressure will decrease and impulsive pressure will increase if there is columns inside the water tank or if there is a baffle wall present inside the water tank. So this figure highlights only the distribution of hydrodynamic pressure acting on the sidewall as well as the base slab. And in the coming slides, we will quantify the pressure values for both the impulsive and convective modes. And I told that there are charts available for circular tanks as well as rectangular tanks for finding out the value of MC, MI, and KC. And it depends upon the geometry. For a circular tank, it depends upon H by D, and for rectangular tank, it depends on H by L. And for a particular value of h by d, assume that it is equal to 1, you can find out what is mc, what is mi, and also you can calculate what is kc. Kc is the stiffness for the convective mode. So all these charts helps in finding out the parameters for modeling the water tank. And this is another chart which I have taken from 1893 part 2. And this chart gives the values of the height of location of the impulsive mass as well as the convective mass. And there are 4 parameters. One is HI, the other one is HI star, second one is HC and HC star. And this HC and HC star and HI stars are to be considered if we are incorporating the pressure or hydrodynamic pressure acting on the base slab also. And sometimes for a shallow water tank, assume that our H by D value is very less than 0.5. So there are chances that this HC star and HI star may increase beyond the total height of water. So in that case, instability may occur. We have to check the instability and we have to provide sufficient anchorage to the water tank. And this table show the importance factor as well as response reduction factor to be adopted for calculating the base shear. And for water tanks which store drinking water and which carries petrochemicals, the importance factor of 1.5 is used. And for unimportant water tanks, we can adopt an importance factor of 1. And for finding out the response reduction factor, if it is a moment resisting frame in a multi-storied building, we know if it is OMRF, we use response reduction factor of 3, and SMRF, we use response reduction factor of 5. But the supporting structure for a water tank, we are using a lesser value of response reduction factor. It can be 1.8 or 2.5 based on whether it is designed as per IS 13920, that is or designed as OMRF or SMRF. And we can calculate the horizontal seismic coefficient for the impulsive mode as well as convective mode separately based on the time periods of the impulsive mode and convective mode. And how to calculate the time period for the convective mode? We know time period is equal to 2 pi into root of m pi k. And from the chart, we have already found out what is MC and Kc. So knowing the value of MC and Kc, we can find out Tc, and for the Tc value, we can find out what is Sa by G. Next, we have to find out what is the time period for the impulsive modes of vibration, and code gives equations for finding out the time period for the impulsive mass. Now this figure shows how to calculate bending moment at the bottom of the board. This bending moment is required to be calculated while designing the side wall. And we can draw the horizontal forces corresponding to the impulsive mass, corresponding to the mass of the side wall, and corresponding to the mass of the cover slab, and we can position it at the CG positions. And I have used the same color for these 3 lateral forces, but I have used a different color for the convective mode because it is vibrating it in a different frequency. And since it has different frequencies of vibration, the horizontal coefficient value will be different. And knowing the values of base shear due to convective mode, impulsive mode, and base shear due to the mass of sidewall and mass of the cover slab, we can find out the impulsive bending moment as well as convective bending moment separately, and we find the net effect of bending moment by taking the SRSS value. And for finding out the SA by G value, we require the time period for the impulsive mode. And for circular water tank, this is the Codel expression for finding out the time period. It is equal to a coefficient Ci into h into square root of rho divided by square root of T by D into square root of E. And all these notations are standard. Ci is a coefficient, h is the height of liquid, rho is the density of the liquid, T is the thickness of the side wall, and D is the diameter of the wall, and E is the modulus of elasticity of the material of the water tank. And substituting all these values, we can find out what is the impulsive time period, and knowing impulsive time period, you can find out SA value. And if it is a rectangular water tank, you can use a simplified equation for impulsive time period, which is 2 pi into root of D by G, where D is the deflection of the side wall when it is loaded by a uniformly distributed load. And how to calculate uniformly distributed load? It is written here. We have to consider the impulsive weight, half of the impulsive weight plus the mass of one wall, and this weight should be divided by B into H to get the uniformly distributed pressure. And if we apply this lateral force on this side wall, it will deflect. And what is the deflection at the combined CG level of tank fluid system? That we have to calculate. Then we have to put in this equation to find out the impulsive time period for a rectangular water tank. But in the case of an elevated water tank, we had seen that the impulsive mass plus the structure mass, we can combine together, and we know what is the stiffness of the staging against lateral vibration, and we can use the standard equation, which is 2 pi into mi plus ms divided by ks to find out the time period of elevated water tank. So knowing impulsive time period and convective time period, we can find out what is SA by G, and from that you can find out the base shear values. And this slide shows how to calculate the base shear. Base shear, we are calculating separately for the impulsive mode as well as the convective mode, and then we will combine using the SRSS method. Assume that we have to calculate the base moment at the foundation level. Then we can draw the lateral forces at various levels. First lateral force is VC due to the sloshing mode. Second lateral force is VI due to the impulsive mode. Then for the sidewall as well as the cover slab, you can use the same coefficient AHI and find out what is the horizontal force due to the mass of the tank structure. Then you can find out what is the horizontal force due to the mass of the staging, and you can position it at a height which is equal to hcg, and then you can find out what is the overturning moment at the foundation level for all due to all these forces. And since we are calculating at the footing level, we have to consider the effect of hydrodynamic pressure which is acting on the base slab. So this equation contains HI star and HC star. Then overturning moments are to be calculated separately for impulsive mode and convective mode. Then the net overturning moment is obtained by square root of mi star square plus mc star square. So after analyzing the structure for earthquake loading, or after calculating the earthquake loading x direction as well as y direction, we have to combine it suitably. And for that, combination rules are given in the code. Either we can use the 100% plus 30% rule for finding out the critical effect on the tank structure, or we can use the SR square root of earthquake load in x direction square plus earthquake load in y direction square. Now let us look at the plan of a circular water tank. If we take the plan of a circular water tank and consider the hydrodynamic effect acting on this side wall, its variation is not uniform. It has a maximum value along this diameter and it has a minimum value along this diameter. But code permits us to use a simplified distribution for the hydrodynamic pressure on the side wall, and we can use a uniform distribution equal to P max. First find out P max, and we can assume that on the periphery the pressure is acting in a uniform way. And if you take a section at this edge and take the variation with respect to the depth, this is the pattern of the convective pressure distribution, and this is the pattern of the impulsive pressure distribution. This we had seen previously. In order to find out the effect of this hydrodynamic pressure on the side wall, we have to do an analysis with the help of a software. So if there is provision for applying this pattern of loading, then it is okay. But if we are doing a manual analysis, we can do manual analysis in the case of hydrostatic loading. But in the case of hydrodynamic loading also, we can do manual analysis if we can simplify this nonlinear variation to a linear variation. So code permits us to use a linear variation for both the convective hydrodynamic pressure as well as impulsive hydrodynamic pressure. And for this trapezoidal loading, there are coefficients given in 3370 so that we can find out the design values of bending moment and shear force. So till now we have seen the variation of hydrodynamic pressure, both the convective as well as impulsive pressure variation, which is acting on the side wall. Next, our aim is to find out what is the magnitude of hydrodynamic pressure at the top, what is the magnitude of hydrodynamic pressure at the bottom. So there are equations given in the code for finding out the impulsive pressure as well as convective pressure acting on the wall as well as the base slab. So how many unknowns are there? There are 4 unknowns. One is PIW, which is impulsive pressure acting on the wall. Then PIB denote impulsive pressure acting on the base slab. Third one is PCW, which is the convective pressure acting on the wall, and PCB, which is the convective pressure acting on the base slab. So there are equations given in the code for finding out the impulsive pressure which is acting on the wall. And this impulsive pressure value depends upon the circumferential angle. Just I have shown the distribution of hydrodynamic pressure acting on the side wall, and its value will be maximum when the circumferential angle is 0. At this end point as well as this point, the pressure will be maximum. And if you put cos phi x equal to 1, you will get the simple expression for the impulsive pressure acting on the wall. And it is equal to rho gh. Rho gh, we know it is the hydrostatic pressure. And since it is impulsive pressure, it is to be multiplied with the horizontal coefficient for the impulsive mode. And to show the variation with respect to height, we take the origin at the bottom of the base slab, and we can calculate the values of QYW from the chart given for the circular tank as well as for the rectangular water tank. So for each and every point on the side wall, we can find out what is the impulsive pressure acting on the wall. Similarly, this figure represents the first mode shape of the sloshing, and for impulsive pressure charts are given. You can find out what is impulsive pressure acting on the base slab for the circular tank as well as rectangular water tank. Now coming to the convective pressure acting on the wall. Just by looking at this chart, we can say that this corresponds to that of convective pressure because the value is maximum at the top and it has a minimum value at the bottom. So this variation corresponds to the convective pressure. And this is the equation for the convective pressure acting on the wall. And this is the equation for the convective pressure acting on the base slab. Both contain some coefficient which reflects the variation along the height of the wall. So you can find out what is PCW and PCP. So we had seen what is impulsive hydrodynamic pressure as well as convective hydrodynamic pressure. And there is one more pressure value which we have to consider while designing the side wall. That is the pressure due to wall inertia. And it is represented by PWW. First W stands for the structure on which this pressure is acting, that is on the wall. And second notation shows due to which parameter it is acting. And that is due to its own self-inertia. And since the forces on the tank structure are associated with the impulsive mode, we are making use of the same coefficient AHI. And since we are calculating the pressure, we are multiplying the weight of the tank. If it is a RCC tank, we have to use the corresponding mass density. If it is a steel tank, we have to use its mass density. That multiplied by G will be the weight. And since we are calculating pressure, we have to multiply it with the thickness. So using this simple equation, you can find out what is the hydrodynamic pressure acting on the wall due to its own inertia. And while designing water tank, we have to check whether the sloshing height exceeds the freeboard which we have provided for the water tank. So the Caudal expression for the maximum sloshing height, here the sloshing height is shown. Since it corresponds to sloshing, the coefficient which we have to use is AHC. And in AHC, we know there is a response reduction factor which we have already used in the denominator. So we have to multiply that value here. And Dmax will be equal to AHC into R into D by 2 in the case of a circular tank. But if it is a rectangular tank, in place of D, we have to substitute the value of L here. So in that way, you can find out what is the maximum sloshing height of the liquid, which we expect during design earthquake. And the freeboard provided should be more than this sloshing wave height. And I have already mentioned that we have to incorporate the effect of vertical ground acceleration also while calculating the hydrodynamic pressure. And we know the expression for the impulsive pressure acting on the wall. And we also know what is the convective pressure acting on the wall. And we had seen the expression for the pressure due to wall inertia. And this wall inertia as well as the impulsive mass, they act together. So in this equation, they are added together algebraically. That is one part of the hydrodynamic pressure acting on the wall. Second part is the hydrodynamic pressure. And third part is the horizontal hydrodynamic pressure acting on the wall due to the vertical acceleration imparted to the water tank. And how can we quantify PV? PV is given by the relation coefficient AV multiplied by rho GH into 1 minus Y by H. Here origin is taken at the bottom of the side wall. So at the bottom, Y by H will be 0. So that the maximum pressure due to vertical acceleration comes to be AV into rho G into H. And at the top, this value will be 0. And in order to calculate the coefficient, seismic coefficient for the vertical component of base excitation, we can make use of this relation, that is Z by 2 I by R into SA by G. This is expression for AH, but we take only 2/3 of that value, that is AV will be 2/3 of Z by 2 I by R into SA by G. And SA by G, we know it corresponds to the relevant period of oscillation. And what should be the time period for the vertical mode of vibration? And if no detailed calculation is available for finding out the time period of vertical mode, code permits us to use a time period of 0.3 seconds. So corresponding to 0.3 seconds, what is SA by G? That has to be substituted here, and then find out what is the pressure due to vertical ground acceleration. So all these effects are to be combined together by SRSS rule to find out the net pressure. And this net pressure value will be different for the base of the sidewall as well as at the top of the sidewall. And we know it will be maximum at the bottom. And once this value is established, you can do a static analysis which combines the effect of both hydrostatic and hydrodynamic effect, and then we can design the sidewall as well as the base slab. And to get the idea of the relative values of hydrostatic and hydrodynamic pressure, I have included some worked out examples which are given in the IITK GSDMA guidelines, which was published in 2007. And about 6 examples were given in that guideline, and 3 of them are elevated water tank and 3 are ground supported tank, and capacity varies from 50 meter cube to 1000 meter cube. And they have done a detailed calculation for the hydrodynamic pressure for the first, fourth and sixth water tank. And we will see what is the relative value for hydrostatic and hydrodynamic pressure. So coming to the first example, it is an elevated water tank, and the pressure calculation all depends upon the geometry of the tank. We need what is the dimension of the tank along the direction of seismic force and what is the height of the fluid. And here the H value is 3 and this horizontal dimension is 3.43 meters. And what is the maximum value of hydrostatic pressure? It is rho GH. So they have worked out the value of hydrostatic pressure, and it comes about 29.43 kilonewton per meter square. And also the value of hydrodynamic pressure is evaluated, and it comprises of the impulsive part, then convective part, wall inertia, and the vertical acceleration contribution. And let us see what is the impulsive pressure acting on the wall. It is coming as 1.41, and this value is calculated at the base of the wall, 1.41. And wall inertia is coming as 0.32. Then convective pressure. Convective pressure is maximum at the top, but it has a less value at the bottom, but that is also considered 0.12 only. And the value of hydrodynamic pressure due to the vertical acceleration is coming as 1.47, and this 1.47 is almost equal to the impulsive pressure acting on the wall. And using this equation, we can find out what is the net design hydrodynamic pressure. It is coming as only 2.27 kilonewton per meter square. And this value should be compared with the hydrostatic pressure. And it is coming only as 8% of the hydrostatic pressure. So what we can infer is, we usually design the water tank based on working stress method. We can go for limit state method also, but if we are designing as per working stress method, permissible stresses can be increased by 33%. Since it is a less frequent event, code permits to increase the permissible stresses. So this 8% increase will come within this permissible stress increase. So we don't have to consider the hydrodynamic pressure while designing the container. This container is designed, if we are designing for hydrostatic pressure alone, it will result in a safe design, since the hydrodynamic pressure calculated is only 8%, which is less than the permissible increase in stress for the materials. But for the second example, it is a ground supported tank. The height of water is 8.84 meters. So hydrostatic pressure is rho GH, which is 86.72 kilonewton per meter square. And the lateral dimension is 12 meters. And for this geometry, the hydrodynamic pressure at the base is coming as 32.3 kilonewton per meter square. And is about 37% of hydrostatic pressure. So it has not significant, it has marginal influence. This hydrodynamic pressure has marginal influence on the design of sidewall as well as baseline. So it is better to consider the effect of hydrodynamic pressure in this case. Now coming to the third example, this is also a ground supported tank. The height of water is 5 meter, lateral dimension is 20 meter. The hydrostatic pressure is coming as 49 kilonewton per meter square, whereas hydrodynamic pressure is 21, which is about 43%. And it indicates that this hydrodynamic pressure has substantial influence on the design of the container. So while designing the component parts of this water tank, in addition to hydrostatic pressure, we should consider hydrodynamic pressure also. And in order to check the stability of a ground supported tank against overturning, and we know the resisting moment is due to the weight of tank as well as weight of water present in the tank. And the overturning moment is due to the lateral force, AH into the mass of the total system. This is a general expression. So our requirement is the resisting moment should be more than overturning moment. Resisting moment is the vertical force into distance d by 2, whereas the overturning moment is the horizontal moment into h by 2. And on simplification, code says that when this h by d ratio is more than 1 by AHI, we have to provide anchorages to prevent rocking or overturning of the tank structure. Now, we will go through the provisions in IS 1893, which we have discussed till now. This is a summary of what we have discussed. The section 4.2 of 1893 part 2 discusses about spring mass model. And now you know that the spring mass model for the ground supported tank is resembles that of a 2 degree of freedom system, and the elevated tank also the spring mass model will be a 2 degree of freedom system. And you know how to calculate the components of that spring mass model, what is Mi, what is MC, what is Kc, and so on. So section 4.2 of the code gives how can we idealize the elevated water tank as well as ground supported tank with the help of a spring mass model. And for doing lateral load or equivalent static analysis for the water tank, we have to calculate base shear as well as moment, and the time period is required for finding out the spectral acceleration value, and the equations for the time period for impulsive and convective modes are given in section 4.3. And the spectral acceleration values should be adjusted with the help of proper multiplication factor for the convective mode as well as for the steel water tank, since the spectrum is given for the RCC water tank. So the damping values are written in section 4.4 of the code. Then what is the equation for horizontal seismic coefficient, AH? We know it is Z by 2, I by R, and SA by G. And in the case of water tank, there are two horizontal seismic coefficient. One is AHI and the other one is AHC. Then we can find out the base shear. Base shear for the whole structure include the contribution from the impulsive mode as well as from the convective mode. That details are given in section 4.6 of the code. Then in order to find out the base moment, we have to multiply the appropriate lateral forces with the corresponding heights. The details are given in section 4.7. Then once we calculate the loads acting in the x direction and y direction, we can combine these forces for doing the analysis, and the combination rules are given in section 4.8. Now coming to the tank structure, if it is subjected to only gravity forces, the sidewall as well as base slab should be designed for the hydrostatic pressure. But if we are considering the effect of earthquake force also, the tank structure will be subjected to hydrodynamic pressure, which comprises of impulsive pressure as well as convective pressure. Those details are given in section 4.9. And in addition to horizontal hydrodynamic pressure, we have to consider the effect of vertical ground acceleration also. That is given in section 4.10. And the equation for sloshing wave height is given in section 4.11. And what is the purpose of checking the sloshing wave height? We have to ensure that the freeboard provided should be more than sloshing wave height. Otherwise, if the tank contains some hazardous material during earthquake, chances of leakage or spillage are there, and that may cause environmental problem, as well as the cover slab. If the sloshing wave height is more than freeboard, the cover slab will be subjected to uplift pressure. It should be designed for the uplift pressure. Then there is one more thing. If the sloshing wave height is less than the freeboard, the distribution for the impulsive mode and convective modes may change. The MI values and MC values may slightly change. We have to account for that also. So in order to avoid all such circumstances, we should provide a freeboard which is less than the sloshing wave height. Then anchorage requirement provisions are given in 4.12 of the code so that we can ensure stability against overturning. And all the sections, that is from 4.2 to 4.8, are required for doing the lateral load analysis or equivalent static analysis. Why we are doing only equivalent static analysis? In the case of water tank, if it is an elevated water tank, the fundamental mode only dominates. We can assume that it may vibrate in the fundamental mode. But if it is very large, very tall water tank, in that case, higher modes may also have some significant effect. In that case, we can go for response spectrum analysis. And the provisions here are used for doing the lateral load analysis. But these values we have to calculate for designing the components of the water tank, that is sidewall as well as the base slab. And we also have to ensure that there is provision for shear transfer from wall to base slab in all connection, like wall to base slab, wall to roof slab, and wall to wall joints. We have to ensure that the connections are designed such that there is transfer of shear force due to earthquake. And code also specifies that if it is a very tall water tank, elevated water tank with tall staging, with staging height more than 5 times the least lateral dimension, we have to consider P delta effect. What is P delta effect? We know the weight of the water plus tank is acting in the vertical direction, and the lateral force due to earthquake is acting in the horizontal direction. And we can say that the bending moment at this level will be equal to H into H. The equation for bending moment, which we had seen in the previous slide, is horizontal force into the corresponding heights. But if it is very tall, this deflection can be a significant value, and due to the deflection due to horizontal load, this vertical force, that is the huge mass lumped at the top of the side wall, has an additional moment at this base level. So we have to consider that P delta effect also if it is a very tall tank. Then we have to consider higher modes also when it is very tall. And this is all about the provision given in the code IS 1893 2014 part 2 for designing ground supported as well as elevated water tank. Now we will see the evaluation of an elevated water tank which was designed as per these provisions. And this is a very large circular water tank, and it is having a capacity of 2 lakh liters. It is a circular water tank, and you can see the columns which are extending into the inside the water tank also. And this is done to provide supports for the cover slab, so that cover slab can be divided into smaller panels and we can reduce the thickness of the cover slab also. The first thing is we have to assume suitable dimensions for the components of the water tank. The components consist of roof slab, roof beam, floor slab, floor beam, walls. Then for the staging, you can see braces as well as the columns. We have to assume suitable dimensions. Based on a preliminary design, you can assume these dimensions. Then we have to do a detailed weight calculation. This is very simple. For all components, you can calculate what is the total weight. Then using our 1893 part 2, we can find out what is the impulsive mass of the liquid and what is the convective mass of the liquid and what is the corresponding heights. These are required for finding out the bending moments. These are the parameters of spring mass model. And to find out the lateral stiffness of the staging, we have already modeled this tank structure in the software. We have used the SAP nonlinear for modeling this elevated water tank. Then in order to find out the stiffness of the staging Ks, we have to apply a lateral force at the combined CG of the tank structure and liquid, and corresponding to that lateral force, what is the displacement for the structure. Then P divided by that delta will give the stiffness of the staging. So if you are doing such an analysis, we are incorporating the flexibility of the braces also in finding out the lateral stiffness of the staging. Otherwise, if you are using considering the stiffness of columns only, we can use the appropriate equations for K. But in order to get an actual value for Ks, you can model the tank structure, then apply the lateral load, some lateral load at the CG position of the system, and find out what is the displacement. P by delta will give the stiffness of the staging. Lateral stiffness is to be calculated. Time period for impulsive mode and convective mode should be calculated. Base shear for impulsive mode and convective mode can be calculated. Total base shear calculated. Overturning moment about base can be calculated. Then we can calculate what is the hydrodynamic pressure acting on the wall, which comprises of the impulsive pressure as well as the convective pressure. And then we have to calculate wall inertia, pressure due to wall inertia, pressure due to vertical acceleration, then find out maximum horizontal, maximum hydrodynamic pressure at the base of the wall. It is coming only as 14.25% of the hydrostatic pressure. So in the analysis of this water tank, we had not considered hydrodynamic pressure. Then the code also says that in addition to analyzing the tank in the fully filled condition, we have to consider the analysis for the empty condition also. And if empty base shear is coming as less than that of the fully filled tank, we can neglect that condition. Then lateral loads at various levels can be calculated. Then we can model this water tank in any software which can perform nonlinear analysis. Then the design, we had done two design. Okay, in order to find out the performance of this water tank uh, uh, due to time history analysis, we have assigned hinges for both columns and beams. Then 3 earthquakes were used, and if we are using only 3 time histories, we have to consider the maximum value, and if we are using more than 7, we can take the average value. And these are the PGA values for the time histories which we had applied for the tank, and we have modeled two we have prepared 2 models for the tank. One is designed as per 1893-1984, in which we have considered earthquake forces also, but the design was done due to the forces which were calculated as per 1893-1984. But another model in which the design forces were calculated based on the provisions in 1893-2014, and we found that there is some that means this model 1 is deficient. Model 1, which were designed as per the pre-revised code, is deficient in the case of the staging component. That is, braces were under design and columns were under designed. So both were subjected to time histories, and we can see for the first time history, hinges are formed in columns as well as beams for the first model, whereas for the second model, we cannot no plastic hinges or damages seen for the second model. But even though hinges are formed for the first model, it is only up to the immediate occupancy level. It has not reached the higher performance levels. And for the second time history, you can see loads of hinges forming in columns as well as beams. So this is not a desirable failure mechanism. We are not allowed for a design which forms hinges in the column. But if we are designing as per 2014 version of the code, hinges are forming only in the beams, and columns are not subjected to any damage. So this is the response due to the third earthquake. And we can quantify the damage coming to this staging in terms of percentage drift, or in terms of ductility demand, or any damage parameter can be used to quantify the damage of the system. And if we are observing any undesirable damage, we can redesign that component, and then again we have to do a time history analysis to see that the undesirable performance is avoided. In that case, we can arrive at a safer design for the water tanks, both elevated as well as ground supported tank. So in order to conclude, I will give a summary of what we had seen till now. First, we had seen what is how can we carry out the non-seismic design as per IS 3370, and how to carry out the seismic analysis of ground supported and elevated water tank, that is also discussed, and idealization of both these water tanks as 2 degree of freedom system is discussed. Then for calculating the lateral stiffness of the tank staging, we have to calculate the bracing beam flexibility also. For that, we have to model the whole supporting structure and then find out the value of lateral stiffness. Then how to incorporate the effect of convective hydrodynamic pressure, that is included in the recent revision of the code compared to the 1984 version of the code. In 1984 version of the code, even though it is mentioning about hydrodynamic pressure, it is not considering the convective part. But as per the recent division, we have to consider both the convective as well as impulsive part of liquid. Then the distribution of impulsive and convective hydrodynamic pressure is represented graphically. And if we want to simplify the hydrodynamic pressure using a linear distribution, code permits to adopt that distribution also for designing the sidewalls. And these are the references which I have used for preparing this presentation. Thank you very much.
Thank you, ma'am. Dear participants, it's open for questions. If you have any questions, please post in the chat box or you can ask. Ma'am, there are some questions posted in the chat box.
Okay, I will check the chat box. Which type of staging is most efficient in seismic prone area? Which type of bracing system is most suitable for elevated water tank due to earthquake effect? I think elevated water tanks are provided with staging, and these stagings before constructing, we check the performance of this elevated water tank, and both the whatever may be the type of staging, it should perform well. We have to do a thorough analysis for the elevated water tank, and if it is performing due to all the analysis, then we can adopt that type of staging. I think there is nothing mentioned about a better staging for an elevated water tank. Whatever staging we are adopting, it should be able to resist the lateral force which may act on that system. That is my opinion, and participants, if they are having more exposure to these type of structures, they can also answer.
So no more questions, I think, Radhika ma'am.
Dr. Venamol ma'am, please can you
deliver the Okay, good evening, everybody. I take this opportunity to thank Dr. Gigi Anna Varghese ma'am. So we had a very nice and informative session today on seismic design of liquid storage tanks. Madam has explained very clearly from the base all the design aspects of liquid storage tanks subjected to both seismic design and non-seismic design. And it was a great information, ma'am. So subjected to IS codes and a great information. Thank you, ma'am. Thank you for sharing your knowledge with us. Thank you.
And I thank all the coordinators as well as participants for their patient listening. May I leave?
Yes, ma'am. Thank you very much, ma'am.
Okay, thank you.
Okay, dear participants, we come to the end of fourth day of our FDP. So tomorrow will be the last day. We have 3 sessions. 2 will be lectures. The third session will be feedback, and there will be an assessment also conducted in the third session. So I've already shared the material which has been given by the resource person. The assessment will be a simple one. Multiple choice questions, 30 multiple choice questions will be there. So it will be during the last session, 2:15 to 4:15, during which time we'll have both the feedback as well as the assessment. So thank you very much for attending all the sessions. So we'll meet again tomorrow at 9 a.m. Thank you.